In OSPF, another common network type is the multi-access network. A multi-access network means several routers are connected to the same network, usually through Ethernet switch. For example, if 5 routers connect to the same switch, they can all communicate with each other. The problem is that if every router exchanges LSA directly with every other router, there can be too much OSPF traffic. To make this more efficient, OSPF elects one router as the designated router, or DR. The DR becomes the main router responsible for collecting and distributing LSAs on the network. OSPF also elects a backup designated router, or BDR. If the DR fails, the BDR can take over. So remember, multi-access network that implies multiple routers on the same network, and that elect DR and BDR, which eventually reduce unnecessary OSPF traffic. The network administrator can control which router becomes the DR by configuring its OSPF priority. This figure shows difference between point-to-point and the multi-access OSPF networks. At the top, R1 and R2 are directly connected. Only 2 routers can use that link, so it is point-to-point. There is no need for DR or BDR. At the bottom, R1, R2, R3, and R4 are connected to the same switch S1. This is a multi-access network because multiple routers share the same Ethernet network. On this network, OSPF will elect one DR, that's the main router for exchanging LSAs, one BDR for backup for the DR, other routers, that's DR others. So the simple idea is the direct router to router link, that's for point-to-point, so no DR or BDR. For multiple routers on one switch, that's multi-access. So we do need DR and BDRs. 2.3.2 OSPF designated router. In a multi-access network, OSPF use DR and BDR to reduce unnecessary LSA traffic. The DR, which is the designated router, is the main router. It collects LSAs from the other routers and distributes them to the network. The BDR, that's the backup designated router, is the backup. It watches the DR. If the DR fails, the BDR becomes the new DR. All other routers are called DR others. There are 2 important multicast addresses. 224.0.0.5, that's for all OSPF routers, which is the router used this to send information to all OSPF routers. And also the 224.0.0.6, this is the DR and the BDR only, which is the DR others send information to this address. Here we have 5 routers connected to the same Ethernet network. R2, that's the DR, is the main router. R3 is the BDR, is the backup for R2. R1, R4, R5 are DR others. Suppose R1 has a new LSA. First, R1 sends the LSA to 224.0.0.6, the DR and the BDR. So R2 and R3 receive it. Then the DR R2 sends the information to 224.0.0.5. This is for all OSPF routers. So R1, R3, R4, and R5 can receive the update. This animation shows how an LSA travels in a multi-access OSPF network. Here, R2 is the DR, R3 is the BDR, and R1, R4, and R5 are DR others. Suppose R1 has a new routing information. So step 1, R1 creates an LSA. Step 2, R1 sends the LSA to 224.0.0.6. This multicast address is for DR and BDR only. So R1 send the information to R2, the DR, plus R3, the BDR. Step 3, R2, the DR, receives the LSA and becomes responsible for distributing it. Step 4, R2 sends the LSA to 224.0.0.5. This address means all OSPF routers. So R2, the DR, send the information to R1, R3, R4, and R5. The main concept to remember is 224.0.0.6 is sent to the DR and the BDR. For 224.0.0.5, that means the DR sends to all OSPF routers. This is why we need a DR on a multi-access network. It controls LSA distribution instead of every router exchanging LSAs directly with other router. This figure shows a multi-access OSPF network. 3 routers are connected to the same Ethernet switch, so they all share the network. 192.168.1.0/24, their G0/0/0 addresses are for R1, that is 192.168.1.1. For R2 is 192.168.1.2. R3, this is 192.168.1.3. Because all 3 routers are on the same Ethernet LAN, OSPF treats this as a broadcast multi-access network. That means OSPF will elect one DR, also a BDR. The remaining routers become a DR others. Each router also connects to its own local LAN. So for R1, that line is 172.16.1.0/24. For R2, its LAN is 172.16.2.0/24. For R3, that is 172.16.3.0/24. Here, OSPF automatically chooses a DR and a BDR because the routers share the same Ethernet network. The election works like this. The highest OSPF priority, that's the DR. The second highest priority is the BDR. If priority are the same, the router ID breaks the tie. In this example, all routers use the default priority, so router ID decides. R3 is 3.3.3.3, so this is the highest number, therefore is DR. R2, the ID is 2.2.2.2, it's the second highest number, so this is the BDR. For R1, its ID is the lowest number, that is 1.1.1.1, and this is the DR other. 2.3.5 Verify DR BDR adjacencies. This command, show IP OSPF neighbor, show your OSPF neighbors and their relationship. For a multi-access Ethernet network, you may see full DR that implies the fully connected to the DR, or full BDR that is the fully connected to the BDR. We also have the full DR other, that is a DR or BDR is fully connected to a DR other. we have 2A DR other. That's the two DR others knows about each other, but they do not form a full adjacency. This output confirms R1's OSPF neighbors. The show IP OSPF neighbor command give 2.2.2.2, that's the R2's router ID. PRI, that's the priority 1. This is for OSPF priority, which is 1. Full BDR, this is for R2. So R2 is the BDR, and R1 has a full adjacency visit. 192.168.1.2, this is R2's interface IP address. For R3, that 3.3.3.3, this is the R3's router ID, priority 1, and then full DR. So R3 is the DR, and R1 has a full adjacency visit. 192.168.1.3, this is R3's interface IP address. This output is from R2, which is the BDR. The show IP OSPF neighbor that shows we have 1.1.1.1, that's the full DR other, and R1 is the DR other. R2 has a full adjacency with R1. There's a 3.3.3.3. This is the full DR. Where R3 is the DR, R2 has a full adjacency with R3. This output is from R3, which is the DR. Show IP OSPF neighbor shows that we have 1.1.1.1 is the full DR other, R1 is the DR other. R3 has a full adjacency with R1. The 2.2.2.2 implies that full BDR. Where R2 is that BDR, R3 has a full adjacency with R2. 2.3.6 Default DR-BDR election process. OSPF choose the DR and the BDR in this order. Step 1, check OSPF interface priority first. The highest priority is the DR, second highest is the BDR. Default priority equal to 1, and the priority range is between 0 to 255. Priority 0, that means it cannot become DR or BDR. Step 2, if priorities are tied, check router ID. The highest router ID becomes the DR. Second highest is the BDR. So how is the router ID selected? If a router ID is needed, we can manually configure router ID, that's the first choice, and then the highest loopback IP address. And then that's the highest active physical interface IP address. In this example, all routers have the default priority of 1, so OSPF used the router ID. For R3, that's 3.3.3.3 is the highest number, therefore it is the DR. R2 with ID 2.2.2.2, the second highest number among 3, so this is the BDR. And R1 has 1.1.1.1, that's the DR other. But there is an important point. OSPF DR BDR's election is not preemptive. This means a router that becomes DR stays DR, even a router with a higher priority or router IT joined later. For example, R1 starts first, and R1 could become DR. Later, R3 join with a higher router ID 3.3.3.3. R3 does not automatically replace R1 as DR. The key idea is once elected, they keep their job. Suppose R3 is ready to DR, R2 is ready to BDR. Later, a new router joins with a higher priority. or higher router ID, it will not replace R3 or R2. Why? Because OSPF does not automatically start a new election just because a better router joins. 2.3.7 DR failure and recovery. When the DR goes down, the BDR immediately takes over as DR. Then OSPF elects a new BDR from the remaining DR other routers. Here, R3 was the DR, but R3 has failed. So OSPF does this automatically. Step 1, R2 was BDR, that becomes DR. 2, OSPF needs a new BDR. Step 3, R1 is the only remaining DR others, so it becomes the BDR. So now, R2 is the DR, R1 is the BDR, and R3 is done. 2.3.8, the IP OSPF priority command. Instead of depending on the router's ID, we can directly control the election using OSPF interface priority. The command is IP OSPF priority and then followed by the value. The priority can be any number between 0 to 255, where 0 means it cannot become DR or BDR. 1, that means this is the default priority. Higher number, that's the better chance of becoming DR. The highest number will become DR, and then the second highest number becomes the BDR. If priority ties, and then use router ID. For example, we configure R1. So first, in the interface configuration mode for R1, you can enter a sample command such as IP OSPF priority such as 100. So R1 now has higher priority than routers using the default priority of 1. So R1 is more likely to become the DR at the next election. 2.3.9 Configure OSPF priority. So here we want to control who becomes DR and BDR. For example, we want R1 to become DR. So in the global configuration mode of R1, first you enter interface gigabit Ethernet 0/0/0. And then now we are entering the interface configuration mode. Enter IP OSPF priority 255. The priority 255 is the highest possible number, so R1 is the best candidate for DR. For R2, we want this to be the BDR, so no change is needed. Priority is 1. R2 keep the default priority and becomes BDR. R3 never DR or BDR. So for R3 in the global configuration mode, enter interface gigabit Ethernet 0/0/0. And in the interface configuration mode, enter IP OSPF priority 0. We change the priorities, but the existing DR does not automatically change. So we use clear IP OSPF process to start OSPF and cause a new election. After the election, R1 becomes the DR because it has the highest priority of 255. This output confirms that R1 is now the DR. Focus on these lines. State DR priority 255. This means R1 is the designated router because we configure its OSPF priority to 255. The designated router ID is 1.1.1.1. This confirms the DR is the R1. router ID 1.1.1.1. The backup designated router ID is 2.2.2.2. This confirms R2 is the BDR. At the bottom, neighbor count is 2. Adjacent neighbor count is 2.